Let's try to understand the one of the question for the AP Physics Mechanics C part. Basically, the question is that state is this is the question. So I'm just read it out from your side, and so let's check it out how well you can understand. First, read it out. I will give the brief idea of that one. So there is a disk that is having the mass m and radius is r. R is the radius for that one, and there is a cylinder that has the mass is the same m only, that has the mass is the same, but it is placed at the r by 2 the distance from the center of the rotation from where it is rotating that one. So this is a cylinder. Right now there is a omega angular velocity relationship that is given over there. So that is omega f is some kind of the constant, 1 minus e small t by capital T. So this is the omega that they given it, that is varying as the time is changing. So we had to be drive the ultimately the with the using these variables, we had to find out the maximum net torque that can be there. So as we know that when the net torque, if I had to find out the net torque is equal to moment of the inertia, that is the total moment of inertia, I will come to that point, into the alpha. Alpha is the angular acceleration that we have it. Right now, because they are the two system that we have it, one is the cylinder, another one is the disk that we have it. So for the cylinder that has the mass is m and center of the rotation is this point that we have it, and radius is r. So we have the total moment of inertia is due to the two things. One is the disk, another one is the cylinder that is placed over there at the r by 2 distance from there. So the moment of inertia is due to the cylinder. It is a vector quantity, so you can add it. So I'm writing C for the cylinder. Uh, and then I'm going to write it for the disk, moment of inertia of the disk, that I'm going to write it. Okay, so the cylinder is, you have to treat like a cylinder is at the point mass at the r by 2 at the distance. So the moment of inertia formula is, by the way, m r square, that we use it when it is any mass is placed from the center of the rotation at the r distance. So then we use it this r distance, mass is placed at the r, so m r square. But right now the cylinder is placed at the r by 2 distance, so the moment of inertia is m r by 2 square, because it is placed at the half of the radius. And the disk moment of inertia of the disk is moment of inertia is half m r square about the center of the rotation. So that you must know about that one. So for a disk, if the disk is fully having the capital M mass and the rotation axis is this way, then the moment of inertia for the disk is about this axis of the rotation is half mr square. So then you had to keep add both of the values. So this is the total moment of inertia that we get it. Then what we had to do over there is, so if you want to note down, you can note it down. And then my next challenge is to find out the alpha. So to find out the alpha, because they are asking in the question the maximum torque, so I had to, because moment of inertia is that we already calculated. To find out the torque, maximum torque, I had to find out the maximum alpha. So this is the maximum net torque. To find it out, I had to find out maximum uh, angular acceleration. To find out the maximum angular acceleration, they have given the omega, because as we know that alpha, what is alpha? Alpha is the rate of the change of the angular velocity. That is angular velocity that they already given it the relations. So let me plug in over there. So And now we had to differentiate that one. So, so this is the total moment of inertia that we get it. Then what we had to do over there is, so if you want to note down, you can note it down, and then my next challenge is to find out the alpha. So to find out the alpha, because they're asking in the question the maximum torque, so I had to, because moment of inertia is that we already calculated. To find out the torque, maximum torque, I had to find out the maximum alpha. So this is the maximum net torque. To find it out, I had to find out maximum uh, angular acceleration. To find out the maximum angular acceleration, they have given the omega, because as we know that alpha, what is alpha? Alpha is the rate of the change of the angular velocity, that is angular velocity that they already given it the relations. So let me plug in over there. So and now we had to differentiate that one. Omega f is the constant, so it will come outside. The derivative of the one is 0, and this is the exponent remain as it is same. And then into according to the chain rule, I had to differentiate again the upper part. So if I differentiate the upper part, I will get 1 by t, because I'm going to differentiate with the small t. Capital T is just a constant. So this is alpha. Then ultimately the alpha expression is come out to be omega f by t e power minus. Now because we had to find out the maximum one, the maximum value of that one is, so if you know that when the exponent graph that is decreasing like this something, so as the time is 0, so actually it is something like this, but we are not taking the time, the negative time. So when the time is 0, the e, this exponent have the maximum value. To get that one, so the e power 0, e power 0 is 1. Anything have the power 0 is 1, so the omega f by t. So that is the maximum alpha. So you can find it out the torque. To find out the torque, the maximum torque, to find out the maximum torque, you can just substitute the value for the a part. To get the maximum torque, I total, and alpha, basically alpha maximum that we have it. So this is 3 by 4 mr square, and alpha that we have it is, so this is the maximum torque that we have it. Okay, that's perfect. So that is how we are going to calculate this one. Now we have the next part of that one. The next part of the question is, consider the friction force that act on the cylinder at the time t is equal to capital T. Indicate whether this force has a tangential component only or radial component only, or both of them. So the thing is, if you see it carefully, So when any particle, or right now this is the cylinder that we are talking about, um, net force or the friction force that is acting on the cylinder that they are talking about. So this is the disk, and this is the small cylinder that is placed at the r by 2 distance from that r by 2 distance that is placed over there. So that is moving. If it is moving, so it had a two type of acceleration. So one is we have the always the we have the one is tangential component, T I'm writing. One is centripetal. So centripetal is also known as a radial component. So I'm going to write it for R because along the radius it is acting. So this is some centripetal force. So centripetal force or the radial force are the same thing. That is V square by R that we have it. That is acceleration that is towards the center, and that is M. So if you plug in over there, the V is equal to R omega. So V is equal to R by omega square. So if I substitute capital R over there, R square omega square by capital R. So basically R omega square that is come out to be. Because omega is not zero, so it is non-zero. So it is a non-zero. So it is there, means it is definitely the radial acceleration or centripetal acceleration towards the center that is there. Then the another one is we have the tangential component. The tangential component is in this case is it is due to the R alpha. Tangential component is R alpha that we have it, and the alpha is non-zero here because alpha we already calculated as the time is passing. So it is the alpha is there, so it is there. So it is also non-zero. So basically you can plug in the value if you want it. So this is the tangential component that is also non-zero. So basically both are non-zero component. There are both the components are there. Now we had to talk about the in the third part of the question, the drive the expression of the linear acceleration of the cylinder at an instant when the angular speed of the disk is that is defined. So angular speed is omega is given at an instant. We do not know at what time it will be. I have to figure out that one. So this is omega, this is they have given that one. And now we have to find out linear acceleration. To find out that linear acceleration, what I have to do is, because right now we discuss about they are the two component and both are non-zero. If they are both are non-zero, the resultant of both these vectors that is come out to be like this. This is the linear acceleration that I'm going to write with the A, because both these component are always perpendicular to each other, 90 degree to each other, centripetal and tangential component. To find out the radial acceleration, that is come out to be square root of tangential acceleration square plus centripetal or radial acceleration square. So to figure out that one first, I had to be, because they have given the some of the condition at what when the omega is omega f by 2. So first I had to figure out the time. So the omega relation we already have it. So the condition is we had to figure out when the omega become omega by 3. Let's try to find it out that value of the time. Omega omega will cancel out. This is 1 by third of that one. So it is minus 2 by 3 if I take to the other side. So minus 2 by 3. So I'm just putting that value only. I'm not finding out the t value. You will get to know because I have to just directly plug in that value in the time expression. So this is the I will get that one. So now let me substitute. This is e power, this whole value is 2 by third. So I can, because I already have this one here. So radial or the centripetal is easy to find it out, because I have to substitute only the omega. Omega value is they already given that one. So it is the 1 by third of omega final. So this is r omega f square by 9. And centripetal is something I had to substitute that value here. I had to substitute that value for that initial. That is omega f. These are just a constant. But the thing is, I had to figure out that one, because the slender is at the r by 2. Sorry, we are finding out for the slender only. So I had to take, instead of r, I had to take r by 2. Please correct that one. This is r by 2. This is r by 2 because the slender is placed at the r by 2 distance. Even in the next part also, they are talking about the slender only. So the actually this is the r alpha, but this r is the distance from the this one. So it is r by 2. So I'm writing that is also r by 2 here. And so this is e. This value is already, we figure it out. That one is 2 by third. We have to just substitute it. 2 will cancel out. And so the final expression, this is not r, this is the total one, that is equal to r omega final by r plus tangential, the component of that one. I have to put the square of that one here also. So r get cancel out. So this is the, if you want to take it out, few the things common, you can take it out. And this is the final expression that we have it. So if you have a further doubt, you can ask to me. So this is the whole story is that we have it. So, okay. So I will attach the PDF of the solution also.